Okay. Okay. So what will happen? These holes, what it is developed in the N side, due to this attraction of these electrons, what is there in the P side, the holes will come in this side. Same thing will happen due to the attraction of positive charge, what is there in this N side, electrons, what is already developed during this photon energy into the P side, it will go into the N side. So what will happen? The separation of electron and hole will be happen. So if I give some load, so electron will come in this side, and we can able to find some current. But voltage, what is already developed into this junction, this is your voltage. Okay, so this is the basic thing of solar cell. But when okay, so now all of you, this is the basic thing of solar cell. So but in practically the solar cell is not like that. Solar cell structure is not a flat. In
Sir, this is just like a photodiode, means.
sir, photodiode is a little bit different. But solar cell is one type of photo detector, you can tell. And solar cell actually the surface. Hello.
Listening, sir. Thank you. Thank you. I'm listening.
Okay.
Please.
Okay. So, but then in the actually the solar cell is not like that. In practical, solar cell is not like that. Okay, I am going to the software first, and parallelly I will try to do. So in the PC1D software, it is there. So one symbol is there, PC1D. 1D. When you just click this, you can able to find one thing. It is called device area. So I am taking the device area 1 centimeter square. This is you can increase or decrease also, but 1 centimeter square is a standard. So no need to change anything. Next is surface texturing. First you go to the surface texturing and you tick both surface. When you are tick both, automatically 54.74 degree and 54.74 degree it will comes in your screen, and it is an optimized value what is proposed by the industries, and it is also proposed by texturization. And depth will be 3 micron. It is also the optimized value, and you do it. Okay, so we did it the both side surface texturing, front and rear also. First of all, we should know what is the need of the surface texturing, what is surface texturing, why we are doing this surface texturing. Suppose what I told, solar cell is a device which will absorb the energy, that means light energy. So if my light is, suppose my surface is flat, in that time what will happen? Light comes there and it will reflect. Silicon, the flat silicon surface, so suppose this is a silicon wafer. In the flat silicon wafer, 30% light will be reflect, 30% light will be reflect, 70% light only it will comes into this wafer. So we have to reduce this reflection, because our main objective is maximum photon or maximum light must be absorbed. Okay, for this reason we have to do texturing. But when you're doing texturing, texturization is a simple chemical method. How it is happen? It is happen with the help of sodium hydroxide or KOH. Yes. So 45% sodium hydroxide and 55% of water with 90 to not 90, 80 degree to 100 degree centigrade. It will take 3 to 4 minutes. It is a standard industry process. I am talking about the industry process. I am not talking about the other process you can able to do. So if it is doing like that, in that time your wafer will be like that zigzag. Yes, it is called chemical etching or alkali etching also. We are using alkali for this reason we are etching. We are talking about this thing. But one thing is there. Yes, the you see that this is 54 degree. The sharp point is 54. You can after this session you can try it with other degree also. You tell after that what the result you can able to find it. Okay. So but the thing is we have to take one big container or beaker. If you are doing this thing in the lab, you have to do with the container or beaker, or if you are doing work in industry, the big containers are there in the industry. Some wafer is there. You have to set the wafer. After that this thing will happen in the large scale. Okay. So but when you're doing it, the not just up surface, the back surface of the solar cell also, it will be etched. You can't protect it because I am talking about the large scale industry. I'm not talking about small thing in the lab. In the lab, with the help of Teflon, with help of other thing, you can manage. But in the large scale, you're not able to do it. Okay. So this is called texturization. So this texturization, after texturization, what will happen? My reflectance reduced to 30% to 10%. Okay. So this is the thing. Okay. Again, I come into the software. Next is front reflectance. Again, it is coming front reflectance when I click it. Okay. So in front reflectance, so what I told you, so already 30% reflectance already there. 30% reflectance already there in the silicon wafer. After that, I reduced to 10%, but still 10% reflectance is there. We have to reduce again. How can I reduce? If you see the solar cell, what is the color of the solar cell when you see the general solar cell in the module? Gray, not gray. It will be bluish black, I think so. Why it is bluish black? Not silicon surface. Actually, what you are seeing the color, it is this color of silicon nitride. We are using silicon nitride as an anti-reflection coating. So on top of this, on the top of this material, on silicon, this texturization, we have to give another coating for reduce the reflectance. Yes, I will tell later. I will come specification later. Now I am not talking about the specification. It is coming in the software. In that time I will tell. Now I am talking about the silicon nitride. So after I deposit the silicon nitride in the industry, now their reflection is less than 2%. Industry. Practically, I did in my PhD, it is about 0, 0.2, 0.3. But industry is not possible because when you are doing with large area anything, it is little bit tough to do it. But 2% is a standard reflection. So what should I do? In the fixed, I am doing with 2%. All of you type 2. Okay, okay. Okay. So another thing I am giving, another thing I want to tell you. If you want to do some research about this anti-reflection coating, or if you want to do some extra knowledge, so in that time you should know how we have to design the anti-reflection coating, or what is the main criteria to deposit the anti-reflection coating, and what is this thing. Actually, suppose this is my silicon surface. So refractive index of silicon is 3.3, and on top of the silicon it is the air is there. Okay, so the refractive index of air, how much? 1. So between 1 and 3.3 you have to deposit such material that reflective index must be between this range 1 and 3.3. So what is the formula? The formula is, suppose this air is a R1, this silicon is R3, my refractive index what I want between these two, it suppose it is R2, it will be root upon 1 into 3.3, like that. Understood? Understood? Any problem? So I have to decide this type of material only. So in this material, not silicon nitride, silicon dioxide is there, aluminum oxide is there, zinc oxide is there, AZO aluminum dope zinc oxide is there, silicon oxynitride is there. So many things are there, but still popular is silicon nitride. Why? I will tell later. But now aluminum dioxide is also very much popular in the industry also. Okay, because this their refractive index lies in between these two range. Okay, so this is the one problem solved, the refractive index. Another thing, how much thickness of this refractive of this anti-reflection coating? How can I measure it? This is also one formula is there. The formula is the thickness. Suppose d1 equal to lambda 0 4 n1. So n1 is the refractive index of this material. Lambda 0 is the wavelength where we want to absorb maximum photons. So solar cell is a device what it will be mostly work on visible range and infrared range, and mostly work on this wavelength 570 560 nanometer light or 550. So you just put in this value, you can able to find thickness will be 75 nanometer or 70 nanometer, like that. Okay, clear everyone? Okay, so next, in this simulation I am not doing this coating. In this coated surface you can do it and you can able to coat it, but now I am not doing it. You can give the thickness of the first layer, second layer, third layer, middle layer, anything, or with anything. When you coated surface you activate it, you can able to do it, but now I am not doing it. I am just fixed my reflectors 2%. Okay, okay, so this is complete. Now region 1 you come, the thickness. So thickness is a one type of research, very hot research topic in the thickness, because 30 years before, not now, Shockley Wizard, Nobel laureate, his group already told that if you want to fabricate good crystalline silicon solar cell, 30 micron is enough. 30 micron. But still today industries are doing the wafer thickness 180 micron. You can ask me why. Why? Because of what I told you first. When they develop the industries, in that time they develop their machineries, everything like that way. Because the thin silicon to find in the market is very much tough. In my PhD, I did what in the starting of my bio told, first fabricator of thin silicon solar cell in India. I did my silicon solar cell fabricated die with 10 micron. But it is not a commercially available this type of wafer. The commercial wafer, what can you able to find? It is 180 micron to 200 micron. So you can write 200 micron. Okay. 10 micron, if you want to design, you can design it in PC1D. 10 micron, 20 micron, 30 micron, you can design. This is not a thing you can do. But now we are doing for standard solar cell. Okay. So now material, go to the material. When you go to the material, there are so many materials are there. But I am now today talking about the only silicon. So I am select silicon only. When you select the silicon, in that time everything about the silicon it will come. You can ask me how it is come. MATLAB programming already there in the file, so it will come automatically. You no need to do anything. Okay. So before that, I already told about the fabric. I told about the texturization process. So everything will come. Okay. So next, you see the doping is coming. P-type background doping is 1 into 10 to the power 16. It is already coming in the software. You can change it. You can change it, but I am not going to change because my standard silicon industry solar cell, it is an industry value. Okay, this doping, P-type doping. But now, what should I do? What should I do now? P-type already there. What should I do now? Tell me. Yes, I have to do the N-type diffusion. First, you go to the N-type diffusion and enable this N-type diffusion. And one thing you should do, don't need to change anything. Just in the sheet resistance, you have to give 50 ohm. Huh? What? Not understand. I will tell. I'll tell. In junction, what happened? And junction depth, I have to give 0.3 micron. When I do this like that, automatically my doping will change. Now I'm telling that if you are working on industry or if you are working on any lab, to find out the doping concentration in the material is very much tough, or some cost effective some instruments are needed. For this reason, one bypass method is there. The method is, you have to, after the deposition of N-type on top of the P-type, you have to check the sheet resistance. If your sheet resistance is near about 50, one relation is there, sheet resistance to doping, you can able to find out the doping. In the industry also, even my lab also, when I start my work, in that time a measurement instrument was not there. So in that time, what I did like that. I have to check the sheet resistance of the wafer like that. 4 probe one instrument is there. In that type, you can able to check it. When it is 50 ohm, it will be a little bit near to the 19. And junction depth also be like that. What is the junction depth? Now I'm talking about the diffusion process. What I told you in the starting, now my solar cell is like that, not solar cell, still it is not solar cell. It is a textured wafer, sorry. On top, I am giving N-type material. This is my N. This is my P. Okay, na? So now, what will happen? I have to do diffusion. Diffusion is happen with the help of one gas is there. It is called POCl3. We maximum companies they are using phosphorus as a dopant. One gas is there in POCl3. So in the industry or in the lab, how can I do it? One chamber is there. This type of chamber. In this chamber, take off wafers are there. I have to give some gases. I have to give some gases. Actually, we have to use oxygen, nitrogen, and also POCl3 in the, but this oxygen, nitrogen treated as a carrier gas. And I have to give POCl3 into this wafer. Now the question is, if I give the POCl3 gas in this whole chamber, it will not deposit on the front side. It will also deposit in the back side also. In the simulation software, this thing will not address, but practically we should know what will happen. So if it is deposit on N side and also into the back side also, so two junctions will be there. It should not be there. Can you tell anyone what we are doing next? Okay, I will tell later, don't worry. So this is the criteria, and this temperature will be 900 degrees centigrade to 1100 degree centigrade. This temperature, it will be there. Okay, so my diffusion part is complete. So second front diffusion also you can do. I am not about the rare diffusion. Now it is coming the recombination. So what is recombination? We first we have to know that. One already participant already asked me about the recombination at the starting. What is recombination? Yes. Recombination means when the lights come into the surface, what will happen? Electron hole pair will generate, but their lifetime will be very much small. Again, they want to recombine with, suppose it's electron is want to recombine with hole again. Same thing, hole also want to recombine with electron again. But our main thing is I have to send the electron in the outer circuit, not inside the material. So I have to protect this recombination anyhow. So this is the another research topic, and very, very hot research topic in the area of solar cell. Many students, many researchers, many faculties, many professors, their whole career they are doing the work to reduce the recombination. So recombination is this thing we have to protect. There are two types of recombination is there. One is called bulk recombination, one is called the surface recombination. The surface recombination is happen due to the surface. Suppose it's happen with any surface. It is not like a semiconductor. It's happen in any surface. So what happened? Suppose when the wafer is cutted, in the suppose this is my silicon wafer. Okay. In the normally if I see the surface is very much polished. Actually, it is not polished. It will be zigzag like that. Already I textured the surface also. So this type of thing is there. What actually happened? Silicon, the atom of the silicon yes, it's like that. So the in the top of the surface, the dangling bonds are there. So when you are going to electron hole pair generated, the electrons what want to go to the, it can be come into this on top of this dangling bond, and we can lose some electrons and current also. For this reason, passivation is needed. This passivation, in the start of my talk, what I told you, silicon nitride, it is not actually only for anti-reflection coating. It is also treated as passivation layer also. It is a dielectric layer and it will passivate the surface. It will passivate the surface also. Yes, tell me. No. Some other technique is there, but if you want to go for very good surface, good lifetime, you have to deposit some dielectric. There is a no. Electronically, it is not possible. Electronically, only possibility is if you deposit some dielectric or during some plasma effect. Suppose if you give some hydrogen plasma, in that time also hydrogen atom will be coming to this dangling bond. It will reduce some recombination. But the standard method is silicon nitride in the industry. Why? Because silicon nitride will do both work. It treated as an anti-reflection coating as well as the passivation layer. For this reason, silicon nitride is so much popular. Aluminum dioxide, the same thing they are doing. Lattice, for the lattice mismatch also, the some thin layer of any dielectric you have to deposit. In that time, what I told you, you have to deposit something. It may be a silicon nitride, it may be a some tunneling thing, but you have to deposit. Mechanically, it is very tough to reduce this thing. Understood? I am not telling it you have to do it silicon nitride only. Other material also you can use. This is in the actually the lattice mismatch will happen when you are going to fabricate the heterojunction. But because we are now doing only crystalline silicon. We are homojunction. We are not going about the heterojunction. Heterojunction, when you come into the, in that time, this tunneling layer, this other thing, it will come into the picture. Okay, I am doing only homojunction silicon. Okay, so this is called recombination. So in recombination, I can reduce with this method, but in the it is if your cell is there is no loss, the band gap what you use in the material, this you can generate, but it will not come. It will not come. If maximum in the silicon 7 in the industry 7.7 it is coming.
So by cascading those curves, we can generate how much voltage will
in that time the voltage will going to add one by one. One cell, it is called tandem cell. This type of cell we are actually using for our space research, because our space research what happened, the suppose much energy is needed in space research, suppose some Chandrayaan 3, the all solar panels, it is in that time multi junction is needed. Why? I needed much more energy, much more voltage. In that time it is okay, because we are not going for, because the fabrication cost will increase. One junction, two junction, it is very much tough to optimize. So much parameters are there in the practically. Simulation we can do anything. 44% solar cell also we can be achieved. This is not a problem. But practically, after 3 years of work in my lab, my highest achieved solar cell is 18%. So many things you have to add. You have to add it. Okay. We have to do, and also you have to go for tunneling also. So many things are there. So it is very much tough in the practically do it, because to optimize the silicon nitride thickness in my lab, I needed 1.5 years. Just silicon nitride thickness 75 nanometer achieved after 1.5 years of work I did. Okay, so this is a little bit challenging. So I am going to relay about this practical and this thing. So bulk recombination. So bulk recombination value I am giving suppose N 1 2 3 and P I am giving 0.0008. So now again the question will arise, why I am giving N 123 and why I am giving P 0.0008? Because the P, the surface specification is there on top of the surface, P region, but N it is not there. Sorry. For N the surface specification is there, but P it is not there. So it value must be less. Okay. So it's okay after that. Now I am giving front surface recombination. So in front surface recombination, I am giving the value for the front, it will be 100. It will be 100 both. Why I am giving 100? Because same thing, in my front side specification is there, my back side there is no specification, but now back specification is a very common, but I am not introduced this back specification. If you want to introduce, you can introduce. So I am giving 100. In rear specification I am giving the value 1000, both S and SP. Okay, so my model already complete. Now I go into the fabrication process. In the fabrication process, what I told you, the after diffusion, this is my cell. This is happen already, it is there. Backside also I can't deny it, my n is there. So this is my n, this is my n, middle it is p. Now what should I do? My next procedure is I have to deposit silicon nitride after that. In the software, at a first stage, I told about silicon nitride, but fabrication after that, I have to do this silicon nitride deposition with the help of, how can we have to, one is process is there, one device, it is called PCVD, plasma enhanced chemical vapor deposition, with the help of two gases, silane and anyone can able to tell? One is silane gas and another is, no, it is ammonia. Okay, so the reaction is like that. Suppose one gas is silane, SiH4 plus NH3. Temperature will be, I forgot the temperature value, a little bit, 300 degrees centigrade, like that. With, so okay, so after that silane silicon nitride will deposit. So now on my front surface is silicon nitride, this is silicon nitride. After that n type silicon, after that p, after that again n. So this is now, it is my device. Now what should I do? Now I have to go for metal deposition with the help of screen printing. In top we are using aluminum, it is aluminum, huh? Oh, sorry, not aluminum. It is in top it is silver. In back it will be aluminum. On top it is silver. Why I am going for silver? For ohmic contact. Okay, now I am deposit the metal contact. Now the problem is, it is my metal. After that dielectric, after that semiconductor. How the electron will conduct? How the electron will transport? Between that one dielectric is there. I will tell later, don't worry. I'll tell, don't worry. And backside, I am giving aluminum. I am using actually aluminum paste. Like your toothpaste, this type of metal paste is available. After that, my device is ready. It is not ready. What is the problem now in my device? First problem, on top of the it is a finger. It is called finger actually. In the finger, metal contact after dielectric, electron will not transport. In the back, already one junction is there. Now we have to do, it is called firing. Firing means thermal shock. High temperature, thermal shock I have to give. In that shock of thermal shock, what will happen? When I give some thermal shock, This metal, what is deposit on top of this silicon nitride, it will come into this, it will touch this, it will touch this n-type region. It should not be cross this n-type region, otherwise it will be, your junction will be not working. It will be shorted. It should not be shorted. It should not be touch p-type. Very, very crucial. This thing is very much crucial in the industry, in the lab also. To optimize this firing, it is very, very much tough and crucial, because only this length is 300 nanometer. Okay, so this is the one work will happen. Sorry, this is the one work will happen in front side. In the back side, what will happen? In the back side, what will happen? Aluminum is a very treated as a dopant of p-type dopant. When actually you are going for firing, this aluminum, this n-type layer, not converted into p-type, it will convert it p plus. So for this reason, I am telling this firing is so much crucial. Why? Because of these two things at a time. Within it is 1 minute it is happened. These two things. So this aluminum now it is treated BSF layer. It is called back surface field. So at a time it's happened during the thermal shock. So now my solar cell is ready. Okay, so I'm go to the simulation again. Small scale you can do, but large scale it's not possible anything, because when you are working with thousands of wafers, thousands of cells, suppose if you go for any industries, thousands of cells they are working, in that time this type of thing is not there. One machine, one machine you have to do like that, everything it will do at a time, because the process you are not able to see, it will be one by one, it will going. Okay, okay, so next I have to go for excitation. I have to give some light. I am giving transient with 16. Now I have to go to the excitation file. One sun, and run it. When you run it, after that in the result section you can able to find short circuit current, maximum power, open circuit voltage, and in this also you can able to find IV curve also. This is a power, this is a current. Okay, again I'll repeat, don't worry. Go to the excitation. It's not coming. In this excitation file, you have to click. Select the one sun. This file you have to select. Open it. After that, you have to select the transient 16. After that, short circuit current is there, maximum power is there, open circuit is there. So you can able to find out fill factor. So what is the formula of fill factor? P max by VOC into ISC. All of you please calculate. Fill factor formula is P max by VOC into ISC. After that, you can able to find out the efficiency of my solar cell. Okay. Chand, any question came from the online? Huh? No, some chat, something they are asking.
Sir, how will see the output?
Okay. NS3, yes. It should be AG on top, AL in the rear. Yes, NS3 350. Yes.
Sir, how will see the output? Before
Okay.
that
Okay. I will tell again. Don't worry.
Okay.
First, in the excitation, you go to this. You see. You first select one sun. Open. After that, run. You can see the output there, and also you click this graph. 4 graphs are there. This is the energy bands, carrier densities, generation recombination, and also IV. It's okay?
Thank you, sir. Got it.
Okay. Again, you go for the device. Now, I am telling that how you can able to do this work. If you want to do some simulation, some design with the help of this software. One thing, what I told you, you can optimize the doping. I am talking about the only silicon. Some other materials also be available. Indium phosphide is there. So aluminum, gallium arsenide also be there. So this thing also you can use. Also, you can use you can optimize the ARC coating with some thickness. You can do. Okay, so we can do it this thing, and you can able to find it. What is the actual thing? Okay, so okay, description of the graph. Okay, see that this graph, solar cell, the direction of the current is opposite of diode. So in the 4th quadrant, I can able to find this current. So my current is about more than 35. It will be 37 like that something. Okay, I'll check once again in my simulation. It will be 0.0374 ampere. Okay, so this is the thing, and my power again, it is the what is thing. This is my voltage. This is my maximum power. Okay. red one is current. Voltage is x-axis is the voltage, y-axis is the current and power. This is the standard IV characteristics of solar cell. So can you tell me what is the efficiency? Anyone calculated? So fill factor, how much you got? 81% fill factor. Yes, it is also a standard. Okay, and here, and what is the efficiency? BOC ISC into fill factor by what is our area? Our area is 1 centimeter square by 1 into what is our watt per meter square. You see that constant intensity. I am using 0.1 watt per centimeter square. You divided by this value, you can able to find it. Okay. Okay. Any question? Any questions? Yes. Interface. Interface between what? Yes. Yes. Metal and dielectric. In suppose in the metal is on top. When I'm giving the thermal shock, this metal actually it is pushed into this dielectric, and you touch the semiconductor. So in that time there is nothing is happen in dielectric. Understood? Dielectric is not taking part. Metal and semiconductor only. If metal is not touch semiconductor, that means your device will not work. Firing, heatings, thermal shock. Actually, what is happen? One tray is there. With some speed, this tray is moving. In between that, we are giving some temperature. Very small amount of time it is going to temperature, but with very high temperature, more than 1000 we are giving. So in that time, it will just punch through to the dielectric and it touch the N layer. Should not be P. If it is touch the P, that means your junction will not work. Okay. Okay. Thanks everyone.
Well, I have one question. I'm actually layman in solar cells. I haven't know anything about the solar cell.
Yes,
Just I read about the photodiode. I asked in the starting also. As per the fabrication, what I have seen, this is exactly same. What I know.
Okay.
So
But
actually,
but photodiode, the junction is really want.
Sorry, sir.
You terms of photodiode.
Yes, sir.
What you want actually? Tell me.
Actually, just because I seen the fabrication of photodiode is also same, right?
Yes.
So what's the difference between the solar cell and the photodiode?
The main difference is photodiode. It is treated as a sensor, nothing else. But solar cell, you need current and voltage and power also. Photodiode, if you detect particular wavelength, suppose it is giving you some current or something, your work will be over. But in solar cell, you have to need some good amount of power.
Okay.
Understood?
Okay. Means the things are same, but little bit
same.
large and small type of thing.
But a little bit many thing is same, but not 100% same. But my actual aim both are different. Photodiode is different, solar cell is different. Solar cell I need current, voltage, power. Photodiode I don't need it. It is treated as a sensor. Simple.
It's just okay.
Or it
It's
sends
switch.
some wavelength of material, it's okay. Even
Yeah,
if you sometimes it is no need of junction also.
yeah, understand, sir. Although the session is very good, sir. What I expected from the last day lecture also the same. Today we are understanding everything. That's the great session. Thank you for your help.
Thank you. Okay. So can I tell bye? Okay, bye. Bye. Thank you.
Thank you so much, sir, for your sharing your insights. And we will have a break up to 1:45. And we thank you all.
What about the next session? Virtuoso?
Actually, my junior, lab junior, he's chatting. Thank you, Arijit. Dada means in Bengali is brother. Big. Yes. Okay.